Good day, everyone. We are starting the day with the second invited talk. Today we have Sara Royuela from BSc. Sara is a postdoc at BSc. She got her PhD in 2018. And she has been trying to push support for critical real-time systems into OpenMP for 5 years, I would say. And, well, the floor is yours. Please explain us about that.
Yeah, so thank you for the introduction. First thing you might wonder why I'm here talking about critical real-time systems in an OpenMP conference. No? Well, the fact is that the type of architectures that we see nowadays in high-performance computing, louder? Which one? Now? Is it better now? Is my heart? Hello? Testing now?
Move it up.
Even up? What about now? Okay, thank you. So, as I was saying, the type of architectures that we see nowadays are not that different between HPC and embedded computing. In both domains, we are exploiting massively parallel architectures with many cores that can go up to 64 cores in the case of the AMD EPIC, as we saw in the Frontier supercomputer the other day. And in the embedded domain, for example, the Calray MPPA coprocessor that goes up to 80 cores. And also in both domains, we are exploiting accelerators for executing image and video processing, for example, in GPUs or computationally intensive application in FPGA. So in this scope of multi-cores and accelerators, OpenMP is kind of alike. It's like a duck to water. So what's the good about OpenMP here? OpenMP offers a good trade-off between the performance it gives and the programmability and portability it offers. Besides that, the incremental approach of parallelizing applications and also the flexibility to define different kinds of parallelism and also different kinds of synchronizations makes OpenMP very attractive to expose the parallel nature of applications, not only in the HPC domain. What's the but? Well, the fact is that the OpenMP specification and also the implementations disregard some aspects that might be crucial when there is certain level of criticality in the system. And here I'm talking about, for example, having a reliable error handling mechanism in OpenMP, which does not exist, although there have been efforts to include this in the specification. And of course, about correctness. So responsibilities on users to produce conforming programs, and OpenMP does not say anything about that. And if we look only to performance, it might be sometimes difficult to compete with pure MPI applications or native CUDA applications in the case of NVIDIA devices. So the good and the bad. But then it comes the beauty. And the fact is that OpenMP is very good at exposing and exploiting the synergies between different domains. And the synergies I'm talking about here are those between high performance, of course, and real-time domains. The requirements in these two domains have been converging over the years. So, for example, energy is not only a concern in embedded computing, it is now a concern also in high performance computing. And the other way around, performance is not only a concern in high performance, because now in real-time systems, we require also high throughput for many applications. So these requirements are converging. And where are they converging? In the implementation of cyber-physical systems. These kind of systems are those that are managing semi-automatic cars, for example, or giant scientific equipment, like giant telescopes, or the systems that combine edge and cloud computing for the management of smart cities. So cyber-physical systems are all over the place. So what do they require? Performance, of course, as I said, because we have complex computations that we need to execute at a high speed. But then we have also other requirements that are inherited from the cyber-physical interactions of the system. So these are real-time. And in these systems, we need that the end-to-end response time of the system, meaning from sensor to actuator, occurs in a certain budget of time. Same happens with power and thermal restrictions because of limitations in the power supply or limitations in the environment. We also need the execution to be within an energy envelope. And of course, safety and security, because we need to ensure the integrity of the system, not only due to errors or faults inside the system, but also errors that might occur because of external attacks. Oh. Many requirements here that are not only performance. It might seem that there is a long road to go to see OpenMP moving from a computing rack into an autonomous car. But it is always darkest before dawn. And let's see, maybe we are not that far from it. Because although OpenMP, even in the logo, sometimes it says enabling HPC since 1997, in the last decade and even before, there have been a significant effort to put OpenMP in real-time systems from many different angles. So there have been efforts to implement real-time systems with OpenMP, soft real-time systems, which are more flexible. There have been also efforts to introduce in the specification or introduce, remove, or change things in the specification to adapt it to the requirements of real-time systems. And the same happens with the implementation because of this decoupling between the specification and the implementation and this freedom that OpenMP gives to implementers. There have been also efforts to modify or to describe what the OpenMP implementation has to do to fulfill OpenMP requirements. So there is people already thinking out of the box in this sense. And the same happens with correctness. As I said, the responsibility of producing conforming and correct programs is for the user. But even though the specification says that, there has also been a significant effort to produce tools that check the correctness of the system, that checks the conformity of the system, how the semantics are expressed. So we have work done already also in this sense. Okay, so the real-time spectrum is very wide. There are soft real-time systems that offer a certain level of flexibility on how things are implemented. And then we have hard real-time systems, which impose tight requirements. Things have to happen at some point, and we cannot miss that point in time. So the real-time systems I'm going to address here have in common that they require certain level of predictability, which can be only predictability in the case of soft real-time systems or determinism in the case of hard real-time systems. So these systems are implemented in a closed control loop that has a tight time window. So from the moment in which sensors are receiving data, which typically comes at a reduced latency, so we are acquiring data very often, this data has to be passed to some computer to perform computations, which might be quite complex at some point. And after these computations, something has to happen in the system. So actuators will modify the environment, and this environment will be fed again to the sensors. So here we have this control loop. The kind of systems I want to address, and here is how real-time systems are modeled so far. So these systems are composed of a set of concurrent tasks, and I'm not talking about OpenMP tasks. The terminology is a little bit confusing here, so I'm going to use the concept of real-time tasks to differentiate it of the OpenMP task. So this set of concurrent tasks are processes at the OS level, are handled by the operating system. and they are characterized by a series of characteristics. One of them is the recurrency. These real-time tasks are recurrent, and they might define different kinds of recurrency. We have periodic tasks, which are the ones that occur every a fixed period of time. And then we have sporadic tasks that happen when some event occurs. A periodic task is a specific case of sporadic tasks in which two instances of the same task can occur at the same time. There is no distance, a minimum distance between two instances of the task. So this is about recurrency. Real-time tasks also define priorities. The priorities, what characterize is the criticality of the task. So depending on the scheduling strategy followed in the real-time system, priorities are defined one way or another. For example, in early deadline first scheduler, the priority is defined based on the deadline. So the closer the smaller the deadline of the task, the higher the priority. Then we have other type of schedulers like rate monotonic, which are based on the period. So the shorter the period, the higher the criticality. The priority. And then we have other kind of systems that change dynamically the priorities of the tasks. Like I don't remember the name now. What they do is at runtime measure the distance between the deadline of the task and how much time the task still needs to execute. And the shorter this time, the higher they increment the priority of the task. So another aspect that is used to characterize tasks is the preemption. Here we also have different possibilities, different preemption strategies. There are systems that are non-preemptive at all. So when a task starts executing, it will end the execution, no matter what priority it has. So the problem with this type of strategy is that if a low priority task starts, high priority task might be blocked for a long time. So then we have the opposite approach, which is fully preemptive. Fully preemptive, whenever a higher priority task comes, lower priority stops, doesn't matter what it was doing, and the higher priority task enters. What happens in this case is that it might occur in high overhead because of context switches and migration. So it can affect not only performance, but also predictability. And because of that, real-time community is converging into a hybrid approach, which is limited preemptive. That the system defines certain points where tasks can be preempted, and if a higher priority task comes, then the lower priority task is preempted. And finally, another aspect of real-time tasks is that they are composed of a sequence of runnables, which are smaller functionalities that I will mention later. So given this information, what is OpenMP offering us to implement this? So real-time tasks, although they are processes at the operating system level, and I will discuss that later, could be represented as OpenMP tasks because the granularity the real-time task is offering matches the granularity expected for OpenMP tasks, in the sense that the overhead of creating and managing tasks in the OpenMP runtime it's adequate to the granularity of the task. Regarding priorities, OpenMP already offers us priorities. The only thing is that they are a hint in the specification, so we just need to ensure that these priorities are fulfilled at runtime, and we are good to go. And then preemption. Preemption, as I said, if we are converging into a limited preemptive strategy, OpenMP is also offering us that because it defines these task scheduling points at certain points in the execution, and then we have the task queue. So if we need to put extra task scheduling points, we have this opportunity. So this is what we have. What we don't have. Recurrency. So we cannot handle recurrency with OpenMP. Okay. So the main obstacle in OpenMP to handle this control loop is that OpenMP is lacking the concept of time. Right? So one way to go is to say, okay, OpenMP doesn't want to do anything with this and leave the user to implement the control loop. This is, well, of course, this is not the suitable option for me because it is an error-prone option. It requires the user to dedicate one thread, one non-preemptible thread to handle time, to handle the periods of the tasks, maybe introducing sleeps in this loop. But this thread could not be the one instantiating tasks, because if the thread instantiates tasks, the sleeps will not fulfill the periods defined. So this solution is not a good option. The other solution is to have the runtime implementing this. So in this case, time should be handled inside the runtime system and should be hidden from the user. And what we need here to implement the control loop is that the parallel region do not end when the threads arrive at the end, because these tasks will be executed again. Remember, they are in a control loop. So if the parallel region is going to implement this control loop transparently for the user, we need to detach the finalization of the parallel region from the sequential execution. And this is somehow similar to what the detached tasks do. The detached tasks do not finish until some event occurs. So we could do something similar in the parallel region and detach the finalization of that parallel region until some finalization occurs, like we turn off the engine, the car, something like that. As I said, real-time tasks are re-instantiated over and over. No? In the case of periodic tasks, the runtime should be the one in charge of instantiating the task whenever the time comes. So if there is some logic in the runtime that communicates with the operating system, which has mechanisms, has timers to define when a period occurs or when a deadline occurs, then the runtime should be the one given a period instantiating that task. In the case of a periodic and sporadic tasks, the OpenMP event-based model is already something we can use. So in this sense, I'm just using attach as an opposite of detach, because in this case, what I would like for the task is not to start until something happens. So if the detach is not finalizing the task until something happens, maybe attach would attach the instantiation of the task to some event. So in the case of periodic tasks, we could have an attached periodic associated with an integer. Maybe it's defining the milliseconds or whatever unit we want to use that has to be used to instantiate the task. In the case of periodic and sporadic tasks, we could just associate to the attached clause an OMP event handle that defines the event to be used. There is something that is not suitable currently in this event model, and it's the fact that the OMP fulfill event defines that the event is destroyed after it is called. So if we are in a system where the tasks are going to be instantiated all over again with the same event, we cannot destroy that event. So we might have some OMP fulfill periodic event or something like that, and the event is not destroyed at the end. And this brings me to the concept of task persistency. So this concept was introduced in 2011 already for the implementation of stream computing operations. In this proposal, what they said is that the tasks, the persistent tasks were instantiated, were created when the enclosing OpenMP context is entered, but they only started execution when they had enough input data in their input channels. So for implementing the real-time system I'm describing here, this concept is almost the same. I just don't need to wait for data, I need to wait for an event, but the concept is the same. And then there is a trade-off in the performance and the use of memory, because if we have many persistent tasks and they are all alive at the same time in the system, we might need some kind of mechanism to handle this and not to have all the tasks alive at the same time. Then another thing is that if we have more than one instance of a persistent task, we need some kind of mechanism also in the runtime to handle these different instances. But this is not the normal case. So let's go to an example, an automotive example. This is an advanced driving assistance system that is used to identify objects and detect potential collisions of the car. So this system acquires data from different sensors, in this case, radars, lidars, and cameras. Then blue boxes, if you can see them, these small ones here are tasks, are real-time tasks. So after acquiring data from the sensors, we have different tasks that process this data, one for each sensor. Then we have another task that associates all the data from the different sensors. And after that, a tracking computation decides the direction of the objects. And after that, a collision module decides whether the objects will be colliding with the car or not. How could we implement this? So I'm just joining what I explained so far. So we have a parallel region detached from finalization. And then inside we have the different tasks for each of the real-time tasks with the corresponding attached clauses defining what is the period or what are the events that have to be fulfilled. And of course, inside the tasks, we will be calling the OMP fulfill event after the execution, so another task can be triggered. So the communication between tasks at this level occurs via events and not via dependencies. And now I'm going a little bit inside the task. As I said, tasks are composed of a sequence of runnables. And runnables, this is a name that is given to a functionality in the automotive domain. So these are functionalities that are characterized by an execution time, a worst case execution time, and also the access they do to labels. Labels are just data. So they are accessing in read-write or read-write mode. And they are a sequence. And the fact that they are a sequence is something that comes because real-time systems used to be deployed in single core hardware. So whatever happened inside a task, it was a sequence. And if they needed to express some kind of parallelism between functionalities, the way to go was separating runnables in different tasks, and then they were exposing the concurrency between these runnables. But if we are using massively parallel systems that not only can handle the concurrency between real-time tasks, but also the parallelism between functionalities, then the access to labels can define, it's exactly the same that we can define with tasks and dependencies, because this is a data flow execution. So going again to the same example, if we zoom in some of the tasks, for example, the radar processing task is composed of 3 different runnables: spatial synchronization, object detection, and depth estimation. So this could be also tasks, and object detection in particular is a very complex algorithm, a YOLO or something like that we could put in a GPU device. And for example, the tracking mechanism is also composed of different runnables. And in this case, these runnables are completely independent among them because each of them is processing a different object. So since they actuate on different data, they are independent. So we could use tasking again to define the relationship between these runnables. So not only host tasks, but also target tasks. And in this case, the relationships between tasks are defined by the dependencies instead of the events. So we have 2 levels of nesting, one for the real-time tasks and one for the inner runnables. But then what happens, because I said real-time systems are composed of a series of concurrent tasks. And in the other slide, I put subsystems because the real-time system actually is composed of different, it has different components, and each of them can be considered a system itself. So for example, we can put this ADAS component inside a more complex use case, in this case, a predictive cruise control, which increases the capabilities of the regular adaptive cruise control that we have in cars. And this will generate like different parallel regions with different components that if we use the mechanism I defined before, we'll end up with different parallel regions independent between them, but the tasks inside these parallel regions will need to communicate among them because the events from one component affect the tasks from other components. And the black box nature of parallel regions in OpenMP is not helping much here. So this is an example of what would happen if we use different parallel regions to implement the real-time system. On the left, you have what a schedulability analysis, a real-time schedulability analysis would expect. You cannot see very well the difference. We have yellow tasks in a parallel region which have low priority, and green tasks in another parallel region, which are high priority tasks. So on the left is what we expect. If at time one, low priority tasks start, whenever a task scheduling point arrives, for example, in time 3, a higher priority task should enter and be executed. What could happen if we have different parallel regions is that when that point arrives, the thread that is executing that region does not see that we have another task with higher priority in a different parallel region. So it will execute the lower priority task. And then the schedulability analysis made at analysis time will not be fulfilled at runtime. And this is a problem. This has also been addressed in the literature. We presented something a couple of years ago, the cooperative parallel for opening the box of this black box of parallels and communicate and share operating system threads to avoid this situation. And there is also other approaches that could be used to ensure that the schedulability analysis is fulfilled, like the free agent threads or helper threads that could enter into play to ensure that the higher priority tasks are executed. Or we can make it simple, although this option is not always possible, and we could have a system integrator that removes all these parallel regions in the different components and generates just one parallel region, and everything will be easier. Different approaches to this. Okay, as I said before, real-time tasks are priority-driven. Schedulers are priority-driven. This means that if the real-time task is defining some priority, all the tasks inside, the other tasks implemented, the runnables, should have the same priority as the parent had. So I'm putting this example here to show how an implementation could fail to fulfill these priorities. It's not just a matter of how we write the program, it's also a matter of how we implement the system. So in this example, we have a high priority task, the first one, that includes another task inside and a task with point, and then another task in the outer level, which is a low priority task that also includes a task with. What happens if the task weight of an untied task is implemented as a loop, which is the same approach that it is used in GCC to implement the task weights in tied tasks. So it could happen that the parent task starts, then it arrives to the task weight, but the children task was already picked by another thread and it started execution. So at that point, since we don't have these task scheduling constraints because we are handling untied tasks, this thread one could be picking the other task, the lower priority task, and it starts executing. And that priority, this low priority task enters the task weight. All this time, the thread is executing the low priority task and the task weight of that low priority task. We are pushing the execution of the high priority task later in time. So what is happening here is that priority inversion is occurring because of this loop implementation in the task wait. So we cannot implement task waits as a loop, for example, in untimed tasks. And then, another thing about the implementation, if we are to follow a limited preemptive approach, as I said, OpenMP is already offering task scheduling points, and there are some of them that cannot be, so these have to be prescriptive, and some of them have to be implemented. And these 4 are the ones that are necessary for the system to be able to fulfill a schedulability analysis. The one after the generation of an explicit task, the one after the completion, the task wait, and of course the task yield. For this, we could use what OpenMP specification is already offering us, the Pragma OMP requires, because this is at the end something about the implementation, not the specification. So we could just say, we require prescriptive task scheduling points, and for priorities, we require prescriptive priorities. Okay, enough about time. There were other requirements that we wanted to fulfill as well. So let's talk a little bit about performance and predictability. So this is a characterization of an engine control system from this paper. These guys are experts on automotive domain. They are from Bosch. And they characterize how an engine control system is. So the number of levels, meaning the number of data accesses, variables accessed, can go up to 50,000. So we have kind of a lot of variables there. The number of runnables we are handling goes between 1,000 and 1,500, which is considerable too. But then the most important thing is the time, the average time of a runnable, because it goes from 0.5 microseconds to 430 microseconds, which is a really, really fine grain time. And then the periods of the tasks go between 1 millisecond and 1,000 milliseconds. So this is what we are talking about for automotive systems. We implemented such a system using OpenMP. We had to do the control loop manually because we don't have the implementation in the runtime, but this is how it would look like. A bunch of very, very fine-grained tasks that occur together in parallel, because we used OpenMP tasks with dependencies to implement the runnables. And then we have these spaces between them caused by the periods. So we measured in LLVM what is the overhead of the runtime to handle tasks. For that, we used a synthetic benchmark that has a series of dependent tasks. So the task dependency graph is just a square of sequences of tasks. And what we have, so we fixed the workload of the system and we increased the number of tasks, meaning the more tasks we have, the finer the granularity of the task. So what we see is that, for example, when we have 10 to the power of 2 tasks, the overhead of the runtime is 0.9 milliseconds to handle the task. Or when we have 10 to the power of 3, it goes up to 1.5 milliseconds. And if we match that with the execution time of a runnable, we see that the current implementation is not suitable because it is introducing too much overhead to handle tasks. So we tried to alleviate a little bit this problem by implementing the concept of task graph. The task graph framework that we implemented in GCC and LLVM, what it does is to record a region of code that can be expressed only with tasks. So that the task dependency graph contains the whole execution of the region. And what we do is, if we can compute that at compile time, we do it. If not, we record it at runtime. And then any time that the region is executed again, we just execute the task graph, meaning that we don't need to execute the user code to instantiate tasks and so on, because they are already in in the runtime system. So we avoid context switches and so on. As you can see, we reduced a lot the overhead of the runtime. Maybe for the case of 10 to the power of 2 tasks, we reached 0.2 overhead, but this is still too much compared to the granularity of the task of the runnables. So there are things still to do here. We could join runnables in a bigger component or try other implementations at the runtime level, like lightweight threads or something like that. Okay, about the scheduling. So everything that we have fixed at the OpenMP level, the mapping between OpenMP tasks and OpenMP threads, cannot be changed by lower levels of scheduling. So to ensure the compliance with the requirements of the real-time system, the only flexibility we have is at that point. After that, we need to ensure that everything is fixed. And for that, we already have features in OpenMP. So to fix threads to cores and to fix that we have one-to-one mapping between OpenMP threads and OpenMP cores. OpenMP is offering the OMP places, environment variable, and also to ensure that threads do not migrate, we already have the OMP proc bind. And of course, the schedulability analysis is based on a fixed system. So if we analyze the system to be run in a 4-core machine, then we need to ensure that the OpenMP runtime is able to get these 4 threads for me, because if afterwards I have less threads, then I cannot fulfill anything. So OpenMP also, in the latest specifications, is including features that help us to define this kind of behavior, like the assumes holds. We could say OMP get max threads equal the number we need, and be sure that this is going to happen. Okay, I don't want to finish without just mentioning again reliability and resiliency, which I already mentioned at the very beginning of the presentation. So OpenMP should somehow ensure the correctness of the system regarding the errors introduced by the user. So if the user defines something wrong, sometimes it's impossible. Sometimes it's impossible to know if the user is relying or not in the order of the execution of tasks or in other aspects. But many other things can be checked, and we should be using these tools to check the conformity and the consistency of the system. Another thing are the errors generated by the runtime. And in this sense, error handling mechanisms should be given to the user to check whether the runtime is giving me the behavior I was expecting. And last but not least, there are other errors, which are errors that can occur because environmental situations like radiation, like bit flips, or other problems that might occur. And in this sense, for example, OpenMP could be offering, which there is already a proposal for that, and we are working also in an extended proposal. It could offer replication mechanisms for the user to define which are the regions more critical that should be replicated, how they should be replicated, and how they should be recovered if something happened in those regions. So this is almost it. The good thing is that the companies that are in the high performance computing domain are also looking at the real-time domain. So any of the companies, here, AMD, Intel, IRM, NVIDIA, they have also sections for real-time. And it could be good to join the efforts and don't look at the two scopes like completely separately. So we have been working on this for many years. As Harald said, you said 5 years, probably a little bit more. And not only me, my group, many people working on that. We have projects going on to develop this. Ampere and Rising Stars are big ones now. We have Ampere is focused on automotive and railway domains. And Rising Stars is focused on telescopes, giant telescopes. So we are trying to push all these things in these projects. And we also have collaborations with companies, which is basic for us because they are actually telling us what they need and how they need it. So we have collaboration with ESA and Airbus in the space domain, with Bosch and Denso in the automotive domain, and with Thales in the railway domain, soon to be Hitachi. And that's it. So OpenMP, enabling real-time since 2020 something maybe. We need things introduced in the OpenMP specification and implementation. We need OpenMP to be conscious of time. We need the event-driven model a little bit enhanced. And we also need some resiliency and reliability mechanisms. We need some things different. So implementation defined aspects are not in the table for real-time systems. So we need to fix how the implementation is going to behave. And we cannot have hints. We need prescriptive behaviors. And also less things. It's not only a matter of adding. If we want to go to real time, maybe 600 pages. Someone yesterday said the number of pages the specification had. So maybe we don't need all these features to start in the real time system. Let's fix the amount of things we need and we go with that. And after that, what we need is to have an implementation that fulfills all this and qualify this to the different standards, safety standards that are out there. And that's it. You want to need to know more, BSC and predictable parallel computing. This is my group. So thank you.
So thank you for interesting talk. So I have two questions. So if each task have the parallel region, so for example, parallel for which is need the several core, how do you schedule those kind of things?
You're talking about tasks in different parallel regions?
Yes.
That are scheduled in different cores. And the question is?
Oh, it's if each task is running in a single core, there's no problem. But if task is need to run the multiple, for example, parallel 4 or something, multiple core, how do you schedule?
So that's the point of using, I'm not sure I'm understanding the question. That's the point of using OpenMP to parallelize the tasks, because when you do the schedulability analysis, you decide where the task goes to be sure that the deadline of that task is met, right? So the current implementation enables the multiple task which include the multiple cores. So that's my parallel region.
So how do you treat it?
Yes. Yeah. Thank you.
Okay.
So usually, in case of the OpenMP parallel 4, we don't specify anything about the number of cores it needs. But in that case, you can change the number of cores to execute the parallel loop according to the situation of the deadline. Yes.
Yeah, but this cannot happen because of how real-time systems are deployed. So real-time systems typically are defined using domain-specific modeling languages that model the system. And there you model not only the software, meaning the number of tasks you have and the dependencies and the events and so on and so forth, but also the hardware. And at this level, at design time, is where you perform verification and validation of the system, is where you do the schedulability analysis. So what the OpenMP system has to ensure is that whatever happened at design time is going to happen. So if at the design time you define a hardware that had 4 cores, then you have to provide a hardware that has 4 cores.
So
Otherwise,
it means that the programmer have to specify the number of cores required to execute the task.
Because the schedulability analysis is tied to the number of cores. If you remove 1 core, the deadlines you were handling might be missed, right? So everything has to be fixed from design to execution.
Okay. And the next question is that what happens if the task include a target directive to invoke some task to the accelerator?
A task includes?
Include the target directive to invoke something in some computation in accelerator.
That's no problem. I mean, in this case, what you need to know at design time is the latency you have when uploading something, and you have to consider that in the timing analysis. But the behavior is exactly the same.
So everything has to be determined at the design time.
Real-time system, yes.
Okay.
Actually, I didn't want to use much time, but in this Ampere project, what we are doing is exactly this. So the real-time system is defined at design time, right? And then we have these parallel architectures to deploy it. So what we are doing is to map. In this case, we are using Amalthea because Amalthea is an AUTOSAR compatible model, but it's open source. What we are doing is to map Amalthea models into OpenMP systems. And by doing this is where we saw that OpenMP perfectly fits in the real-time domain because of how tasks are handled.
Thanks for the talk. It was actually quite interesting. And I have multiple questions. I'll ask one now and see later if they're, otherwise I'll find you later. So you mentioned this static analysis to build a task graph, to resolve dependencies, all the good stuff. How robust is that, or what is your ambition with deploying that? Because that's one of the many things you mention in terms of real-time systems, but we could use that in any OpenMP system at the end of the day, and which gives you, the ability, like if we build that, continue and deploy it, we get a stable system that actually works, and we find all the errors with all the existing codes, and then you guys can use it for real-time systems, and everyone else uses it for whatever they do. So what's the plan with that? What's the status, and how can we actually ship that?
So it is in LLVM implemented. We started implementing it in GCC and everybody was complaining. So we decided to move to LLVM, and now we are fully LLVM. And okay, just before summer, we had a meeting with some people from the OpenMP language committee, with Tom Scotland and someone from NVIDIA. I'm forgetting the name, and Alex Duran and Jeff Larkin. Thank you. Yes. And the feeling was good. So the problem is that we have tested it in host tasks, and then when you mentioned that, the answer is that nobody's using host tasks. Okay, we are trying to fix that. Exactly. Exactly. So I got the feeling that the idea was attractive for offloading more than for host. So we have implementation. We have an implementation of this task graph framework. What it does is, if it can generate task graph at compile time, it does it. And typically in high performance computing, this does not happen, but in real-time system, you typically know what is going to happen. If it is not possible, then we record the system at runtime, and every time this executes again, just the runtime executes the thing. And we are getting good results. for high performance computing applications like kernels. We are using that in kernels like Cholesky's and SparseU and things like that. And this is already there. We just need to push it. And I know this is what you want. We need to push it into the LLVM community. We are now working a bit separately because we don't have so much manpower to do it. But we'll try. Okay, we'll talk about it later. And then another thing I didn't mention because it's, well, so many things that we are doing. When we can generate this task dependency graph at compile time, we also implemented allowing that instead of using the OpenMP runtime to execute the graph, it uses the CUDA runtime to execute the graph. So we are transforming OpenMP DDGs into CUDA graphs. And this is also pretty cool because it accelerates the execution.
So we have two folks in the Zoom who raise hands. So Abid.
Yeah, thank you. Thank you for the talk. It's so really interesting. So I have two general questions. Like one thing is you talk about the advanced driving assistance, so real-time system. So how you feel that the OpenMP scope, because these systems are more towards edge computing now. So do you feel any space for OpenMP programming model in this area, like edge computing? Because edge computing in somehow is a real-time system. And the other thing is, like you mentioned about the commercial applications. What about the scientific applications, real-time application? Like, you know, the CERN, Hydron, and we have at Brookhaven National, NSLS and synchrotron, which do use these real-time systems. And I feel that OpenMP at the some level, at the device level, OpenMP has some application. So what's your feedback on this thing?
So regarding the first comment, so edge computing is so suitable for OpenMP because you are in the node. And the feeling we get from not only from the vendors, but also from the cities. We have projects also for the implementation of smart cities. And we have been using OpenMP inside the edge to execute complex operations there. So the feeling is that there is interest on the system because currently what they have is ad hoc solutions that are very complex to migrate to other systems. When the hardware changes, then everything has to be redone again. And it is very attractive for them to use OpenMP. So the feeling is that there is interest on that. And regarding your second comment, we do as much as we can. So we got in contact with companies interested in our approach. And so far, we got this relation with Bosch and with Thales and with Airbus and so far and so on to implement the system. But I would be really happy if other people provide applications that we can tune and that we can experiment with to use our frameworks.
Thank you.
Good. We have also Greg on Zoom.
Yeah, thank you. I hope you can hear me okay. I like the chart that shows the types of real-time systems that you guys are targeting. Could you put that up there, the line that shows the different types? My question is really kind of basic. What's the alternative to OpenMP? I mean, I think you're doing somewhat of a research project. What is the current state of the art for multi-core systems? For example, is pthreads heavily used? What's the current state? What's the alternative that OpenMP would displace if we had all of the capabilities that you talk about? What's the current state of the art is my question.
So the state of the art is either they are sequential and they know they cannot be sequential because they are not giving the throughput they need, or they are using for example, in automotive, they heavily use pthreads for doing that. And other systems are using programming languages like Ada that allow to express concurrency as well and fulfill real-time requirements because the language is done for that. So this is what I know on the domains that we are working.
Okay, good. That's a good answer because that answer says, is it worth the time to kind of do OpenMP? Because OpenMP is obviously more attractive than those solutions that you mentioned. So I see the point, but I think that that's important. If there's something good enough, then there's a lot of effort to make OpenMP, a real-time support. So yeah, good presentation. Thank you.
I agree, but baby steps. I mean, as I said, it might be a long road, but to have a minimum viable product, I don't think it's going to be that hard. And besides that, Ada community might not agree with what you say, but they know they lack some things. And actually, I've been in contact with the Ada community since I started my PhD. And they are including OpenMP features in Ada. Actually, they are implementing parallelism now, like in the form of loops and reductions. And I know that Ada Core implemented a runtime system based on OpenMP to schedule their tasks. So
I'll try to phrase it such that it might not be too long. You mentioned as problems, OpenMP has all the different compilers, all the different runtimes. And if you want stability, having, different implementations that have different constraints that, is probably not a great thing. Is the plan to say, we'll take one compiler that will be the real-time OpenMP compiler? Or is the plan to say, we'll try to come out with an approach that we can, have a sham layer over the existing runtimes, all of them, and then our own runtime, like the real-time OpenMP runtime, is compatible with all of the existing ones. What are we looking for?
yeah, the way it goes is that you have to qualify the software. If you want an OpenMP system to be flying a plane, you have to qualify that. So you need the...
For the record, I do not want that.
Okay.
No offense, but at least not anytime soon.
Maybe we are not at that point now, but why not? You just need to qualify.
Yeah. So that's fair, and I get that. So the plan is more on the idea, like, let's first maybe as like you guys or like community or whatever will develop both the standardization parts, but also a real-time runtime that we can then verify, and then we maybe at the beginning we share it, or we always share it. Why would we compete on it? I don't know. Is that kind of more the direction? Let's build a single new OpenMP real-time runtime first. Is that kind of the plan? I'm very afraid to take something that we have and try to, compete. And then the goals compete, right? The thingies that we have right now have different goals. And it's not only performance. It's also, if you shimmy something else in, complexity grows. And they already provide all the features we actually don't want for this. As you said, let's start with, 5 features rather than 500.
Mm-hmm.
So I'm a little afraid of reusing something we have.
Okay. Yeah, not reusing as it is, but reusing the knowledge we have in there.
Fair.
Right?
Cool.
So yeah. I would like to have a KMP runtime. Say, I don't want this, I don't want this, I don't want this. I stick to the things that I want.
Okay.
And then I try to make it like real-time compliant.
Okay. That sounds...
That for me is like the
let's give that a shot. That sounds reasonable.
Good time, Ramat. So let's thank the speaker again. Thank you, Sara.